Hi everyone, hope you're all doing well. This is probably going to be a bit of a shorter video, but I wanted to make a few comments on how the falsifiability and the predictive power of some physical model are linked with each other, and what this means for developing those models of physical systems and identifying the causes of some sort of phenomenon that we can observe in nature. So again, this is going to be expanding on some of the things that I've talked about in earlier videos, but let's again just remind ourselves that science involves proposing models of observable phenomenon that have predictive power. So my model has to be able to make predictions for the outcomes of some kind of future observations or some kind of future experiments. If I give you some starting conditions, some experimental conditions, that model has to be able to make predictions about what the outcome of that experiment is, and then we can put those models to the test. If we're making a specific prediction, we can then test that prediction and give that model the opportunity to be falsified. So these models, again, must be falsifiable. So let's remind ourselves what this falsifiable term means. So for falsifiable, this does not mean that the model is false, or if I make a falsifiable statement, it does not mean that that statement is false. What a falsifiable statement is a statement where if the statement were actually false, I could experimentally show that that statement is false. So if the statement were false, I could show it is false. So, for example, the statement, "There are 5 fingers on my hand." Well, that is a falsifiable statement because if there was an extra digit or I lost a finger or something, I could observe my hand, I could count up my fingers, 1, 2, 3, 4, 5, and I could show if I did not have 5 fingers, I could actually experimentally verify that. That's what we mean by a falsifiable statement, and the predictions that these models make have to be falsifiable. There has to be some way where we could potentially show that that model is wrong if in fact that model actually was wrong. So again, if I have some set of experimental conditions, the model should be able to predict a specific experimental outcome. And then if I do that experiment and I get an outcome outside of the range of what my model predicted, well, that model has some errors. I have falsified that model, and I either have to revise that model or reject that model entirely until it can make accurate predictions. Now, we do have to recognize that any measurements we make, both of the starting experimental conditions and the experimental outcomes, any of those measurements still have certain levels of measurement noise. We've talked about how all measurements are going to have some level of error in them, either random errors or systematic errors. But what we want to do with these models is the more specific the prediction, saying, I have this experimental setup, if you have this these starting conditions, this should be the outcome of the experiment. The more specific we can make that, the less likely it is for that prediction for that result to actually have happened just by chance. If I have a very, very specific result, it's going to be very unlikely that I would have gotten a very, very specific result purely by chance. So the more specific our prediction, the more impressive the test, because we are giving it more opportunities to be falsified. And if I have a model that I subject to repeated testing and I fail to falsify that model, well, then I've got a pretty good model. So I want to talk about how falsifiability is directly related to predictive power. The more I potentially could falsify this model, the better the predictive power of that model is going to be, assuming that it is passing the tests that we are applying to that particular model. So let's look at this as a quick kind of a toy example. Let's say I have some competing models on what the outcome of some experiment should be. So let's say I have some experimental conditions. This is going to be just some arbitrary experiment. And there are a couple different conditions that we can start with. Let's say conditions A, condition B, and condition C. Maybe I'm dropping an object and seeing how long it takes to fall. Well, my experimental conditions might be how high up did I drop that object from? Maybe those are my different experimental conditions. And in a good model, each experimental condition ideally should have its own unique predicted outcome. Now, depending on the system, it might not always be an exactly unique predicted outcome. For example, if I have an oscillating system, well, it'll go back to its maximum point repeatedly at regular intervals in time. So if your model is predicting when should it be at that peak value, there would be a whole set of times that it could do that. So that's model one, where we have experimental conditions and then specific predicted outcomes. Let's say we have got another model that is a little bit less specific. So if we have these experimental conditions, model 2 might say, well, either outcome X might happen or outcome Y might happen. It's less specific than we had with this first model. And just for the sake of simplicity, let's assume that these predicted outcomes for whatever experiment we're doing, these are all-encompassing. These cover the entire range of possibilities of things that could happen. So there's no other possible outcomes than either one of these outcomes, X, Y, or Z. Model 2 is, as you can see, less specific. If we have condition A, this model says, well, I don't know if it's going to be outcome X or Y, but it should be one of those. If I have experimental condition B, it should be X, Y, or Z. We don't know which one it's going to be. Okay. Option C, we know it's not going to be X, or predicting that it's not going to be X, but it could be Y or Z. Notice this one doesn't make as specific predictions, so it's going to be harder to falsify. In the first model, if I have experimental condition A, if anything other than X happens as the outcome, that model has been falsified. Okay. So this one, if I do experimental condition A, if I get anything other than X, the model is wrong and I can discard it. For experimental condition B, if anything other than Y happens, my model has been falsified. Okay. But model 2, it's a little bit less specific, so it's going to be harder to falsify. Let's say I have model 3. This model would be an example of one that is unfalsifiable. We're assuming that X, Y, and Z, they cover the entire range of possible outcomes. Like say, this is, I'm dropping an object, and let's say X is the object falls down. Let's say Y is the object flies upwards, and Z is the object stays there. Well, assuming it can't go side to side, that would be all the options. It goes up, it goes down, or it stays in the middle. Well, model 3, this is unfalsifiable. There is no possible outcome, like if I do experimental condition A, there is no possible outcome that could falsify that particular model. Okay. Same with B or C. If I do experimental condition B or experimental condition C, there's no potential outcome of that experiment that would falsify this model. So that model is unfalsifiable. The argument that I would make here is that the more specific the predictions, the more useful the model. Okay. What do I mean by useful? Well, let's say I am trying to develop some new kind of technology, some device that serves some function, some purpose. And let's say I want that device to, when I press a button on this device, it does Y, this particular outcome. Well, if I'm using Model 1, I know specifically if Model 1 has lived up to all of its testing, if I want the device to have an outcome of Y, I know I have to set it up to with the experimental condition B. B matches up with Y. There's no other outcome that will produce Y, and Y will not be produced by any other outcome. This model is very, very specific, so it's very, very useful. If I was using Model 2, and again, I want outcome Y to occur, Well, I could do any of these experimental conditions and maybe it will give me Y, but maybe it will give me one of these other outcomes as well. I'm not going to be able to specifically predict how to set up this object to get a very specific outcome. And that's one of the things that we want to do in science is develop these models of nature so we can make predictions about how different kinds of physical systems will actually act, how they will perform, what sort of what sort of results we expect to get out of that experiment. We can also say the more specific these models, the better we're going to be at identifying causes. So let's say I'm looking at these models, and let's say I have some experiment. I'm not sure what the original experimental conditions are, but let's say outcome X occurs. So let's say we get outcome X, and I want to know what were the experimental conditions that led to this particular outcome. What was the cause of X? Well, if I'm using model 1, so let's say I have model 1, well, the only experimental conditions that should give X as the output is just experimental condition A. So the condition would be just condition A. I can identify that whatever experiment we're doing, experimental condition A should lead to that outcome X, is the only thing that could have caused that outcome X. Okay. What about model 2? If I'm trying to use model 2 and I say, well, my outcome was X, what must have been the experimental conditions? Well, it might have been A producing that outcome X, or it might have been B. We don't know yet which of these two experimental conditions actually led to that particular outcome. So this could be A or B. We don't know which one. Our model isn't specific enough. And for model 3, well, it's unfalsifiable, so any of these experimental conditions could have any of these predicted outcomes. So for model 3, we have no idea. Model 3 gives us no information whatsoever about what might have caused outcome X to happen. So this is, again, what I'm trying to do here is link these ideas of, is my model falsifiable? Model 1, it made very, very specific predictions, and it has the best opportunity, the strongest opportunity to be falsified, because it makes such specific predictions. If you do A, you will get an outcome X. If you do B, you will get an outcome Y. If you do C, you will get an outcome Z. But these other models are much less falsifiable. A, well, it could be X or Y. We don't know which one of those outcomes it's going to be, so it's harder to falsify that because it's less of a specific prediction. And in these models, being able to quantify both the experimental conditions and quantify the outcome make those models much more specific. This is why math is used in science. Being able to quantify what are our initial conditions. So for example, if we're doing an experiment with me dropping objects from a different height, and I want to say, well, at what height, how high up will it be? If I drop it from different heights, how long will it take to hit the ground? Well, if we want to be as specific as possible, those experimental conditions would be the height, which we can measure and have a specific measurement for that height. And if I have that specific height, we can build a model that makes a specific prediction for exactly how long that's going to take. Using math allows us to, again, quantify both the experimental conditions and the outcomes of that experiment, so our models can be as precise as possible, giving them the best opportunity to be falsified. So if those quantitative, very specific models survive repeated testing, are able to make predictions that match with the observations, even though those predictions are very, very specific, that makes for a very, very good model. Let's look at another example of this. Let's do a chemistry example in trying to identify what is the cause of the outcome of some experiment. Suppose I do an experiment where I mix some granular chemical, so something like salt or some kind of powder or something that has kind of a granular quality to it, to some liquid, and there's a reaction. Maybe there's a little fire that starts, it goes through some reaction, there's a certain energy output, something like that. And let's say I go back the next day and I try to set up the same experiment. I take this granular chemical, I take these liquids, I mix them together, and I get a similar but somewhat different response. Maybe the reaction is a little bit more energetic, maybe the colors of the flames are slightly different than they were. Something has changed in the first case and the second case. Well, we might want to ask, what might have caused this change between my first experiment and my second experiment? And how can we tell if that proposed cause is actually the cause or likely to be the cause? Can we start investigating this at all? So I recommend pausing the video for a second and thinking what might have been different the first day and the second day with some of these experiments, and how would you test for that? So I recommend pausing the video here. Okay, so I'm going to move on. Well, what if the temperature of the room was a little bit different? Maybe on one day the temperature was a little lower in the room, maybe the next day the temperature was a little higher, and that higher temperature allowed the reaction to run a little bit differently. So that could be the cause. How would we test that? Well, we could set up our experiment and then measure what is the temperature in the room and do the experiment. We can go to a different room with a different temperature, redo the experiment. We can repeat this experiment for a lot of different temperatures and start to build a model of how does this reaction depend on temperature. But again, we have to be able to quantify what is the temperature in the room. We have to be able to measure those experimental conditions. Well, what else might have affected the reaction? Well, maybe the pressure in the room was different. Again, from day to day, the air pressure changes by little bits depending on the weather and pressure fronts in the atmosphere. Well, we can do the same thing. We can investigate this potential cause by running our experiment under these different experimental conditions. So testing out a whole bunch of different pressures and building a model to say, well, how does pressure affect this system? If we find, at one pressure it does this, and at another pressure it does this, well, that might be a more plausible potential cause for how this reaction is running differently. What else could we do? Maybe the amounts of chemicals that are used on the first day and the second day were different, or maybe the relative amounts of chemicals. Once again, we can quantify this, we can test this under various conditions, and see how does the amount of those chemicals actually affect the outcome of the result, and we can improve our models. Maybe the grain size of whatever material that I'm using. Maybe we were using large grains the first day, and there were smaller grains the second day. I can test that by taking a mortar and pestle and crushing that material up into different amounts. Maybe the chemical concentration of whatever this liquid is. Maybe the second day it was a higher concentration of this chemical or a lower concentration. And again, we can test that under a variety of different conditions. So for all of these proposed causes of why the experiment ran differently on the first day and the second day, we want to test each of those proposed causes by saying, I'm going to do controlled experiments where I change one variable at a time. I'm going to see how I can change that temperature each time and what sort of results I get at different temperatures. Same thing for pressure, same thing for the amounts of chemicals. All of these causes we can test out because we can measure all of them. What if I said the reason that the reaction ran differently the second day was due to the influence of a ghost? would we be able to do that same kind of test? When we said maybe temperature is the culprit here, we said, let's test this reaction under a variety of different temperatures. We can measure the temperature, we can see how that affects this reaction. Do we have any method of measuring or even detecting the presence of ghosts? Because if we were to claim that that was a cause, we would only be able to investigate that if we could have some method of detecting the presence of a ghost and then saying what happens to a reaction when the ghost is present, what happens to a reaction when the ghost is not present, or if the ghost is happy or angry, or I don't know how ghosts work, but the problem is we don't have the methods to do that. We don't have any tools that would allow us to actually put this proposed cause to the test. This is related to something in science called methodological naturalism. Okay? Current scientific methods don't have the ability to quantify or even confirm the existence of anything supernatural. Again, if we were saying the temperature of the room was affecting, if we were saying the temperature of the room was affecting this, we have ways of measuring temperature. If we were saying the pressure was affecting how this reaction happened, we have ways of measuring pressure. Amounts of chemical, grain size, chemical concentrations, we have ways of measuring all of those things. But for proposed supernatural causes, we don't really have any reliable methods to actually either even confirm those, much less measure their particular properties. And one of the problems with trying to add a supernatural element to some model is that supernatural element, because we have no way of being able to test it, tends to make these models unfalsifiable. So for example, let's say I have model 1 where if I have experimental condition A, the predicted outcome should be X. We have a specific setup and we have a specific predicted outcome. If I get anything other than X, well, we know that our model is wrong. If I have model 2 that includes the effect of a ghost, so the experimental conditions are experimental condition A plus the influence of some ghost, I don't know how you'd build any kind of model on what the predicted outcome should be. I don't know how ghosts work. So this destroys our ability to make predictive outcomes. It is unfalsifiable. Saying that we've got this supernatural element involved is unfalsifiable. That destroys predictability, and that really destroys the usefulness of the model. Okay? And this is why science relies on this methodological naturalism, that we only have the tools right now to be able to test and investigate natural, physical potential causes. Those are the only things that we have the ability to measure. Those are the only things that we have the ability to test in these particular ways. Now, it is important to remember that this does not necessarily mean that nothing supernatural exists. If I were to say that nothing supernatural exists, well, I would be claiming to falsify something that is, as far as I could tell, unfalsifiable. We just don't have any substantive evidence that anything supernatural actually does exist. We don't even really have any reliable, agreed upon methods to even investigate the supernatural. So, as far as science is concerned, since we don't have any current methods to identify anything supernatural, we cannot include those potential causes in some of our scientific models. This statement where just because we can't falsify the unfalsifiable, we can't necessarily say that nothing supernatural exists. If we don't have any substantive evidence that it does, I kind of agree with the philosopher Hume's one of his sayings is that we should proportion our confidence in a claim to the strength of the evidence being provided. So if we don't have any substantive evidence for these kind of supernatural causes, we shouldn't have any confidence in their existence. So again, I know we kind of jumped around a couple of different topics here, but I hope that was at least, somewhat interesting, linking together these ideas of falsifiability and predictive power and what that means for identifying causes of certain scientific outcomes and kind of saying what we can or cannot do, talking about supernatural effects. So we're going to call that good for today. Thank you for your kind attention. As always, if you have questions, please let me know. Throw them into the comment. Throw it in a comment there, and I'll try to answer as many questions. As always, when you're discussing ideas with other people in the comments, try to be respectful of other ideas, and try to use these best scientific methods. We'll call that good for today, and have a good rest of your day.